All right. Well, so my name is Jesse Coe, and today I'm going to be presenting a paper called Post-refinement method for snapshot serial crystallography. It's by Tom White, who, as many of you know, wrote the crystallography suite of programs. And so this is actually about one of the newer additions to that. So to start off, kind of briefly, what I'm going to go over is what's the problem, what's the point of the content of this paper. Then I'll go over some of the concepts that arise in it. Some of them I wasn't familiar with, so I'll follow that with kind of the meat and potatoes, the methods and results that were discussed within the paper, and I'll finish up with future applications, so kind of where is this going moving forward. So to start off with, this is mainly to address data challenges within SFX. What are these? So some of the main ones that are pertinent here are that we have different size crystals. Due to the serial nature, every crystal is going to be different, and we can have as tight of homogeneity as we can make on size, but they will certainly be different from crystal to crystal. Next is, as we're all familiar with, the orientation is going to be unrelated. So since we're taking snapshots, we're unable to do a rocking curve or kind of a rotation. So that's another thing that adds to it. Also, our beam at an XFEL has a lot more variance with its parameters compared to a synchrotron, so it's not quite as stable. So we do have to take that into account as well. For each snapshot, there is going to be a variation within basically the intensity and the divergence as well. So how do we get around this? Well, we use Monte Carlo, and so what that means is we're going to essentially have very high redundancy so that we use the central limit theorem. This means that if we take a big enough sampling, we should have some kind of curve where we get average values that are comparable. And the more statistics we have, the higher redundancy. We're able to compare between Bragg spots. For example, we can compare their structure factors. So redundancy is king. So what's the problem? We've basically we have a lot of data. We need to take high redundancy, but we've been doing this, so this seems to have worked. So why move forward? Well, we want more from our data. We want to get as much out of it as we possibly can, and so one way to do that would be taking into account partialities, and so I'll get into that in a minute. But after we do our kind of normal processing where we take our hits and then we index them, we assign HKL values. So we have a rough idea of our geometry as far as the beam and the crystal. But as I said, the beam parameters are going to vary. It's not quite as stable as synchrotron. And the crystal orientation, we may know somewhat which angle we're looking at, but it doesn't mean that we know it precisely. And the more precisely we know that, the better our data is. And so with the initial indexing at this point, we have no way to guess the geometry more accurately in each image. And by this I mean kind of where are we on each reciprocal sphere? Which part of it, which fraction are we measuring? So the program that this paper is essentially describing is called Partiality. I'm not sure if that's how you pronounce it, but Partiality. Okay, I'm being corrected. So this is essentially introducing post-refinement of geometry into serial crystallography. And so what do I mean by that? Like I said, this is exaggerated for your viewing, but the exact angle that the crystal is being hit by the beam could vary from shot to shot. Also, the crystal, we know its orientation after indexing to this to an extent, but there could be like very slight rotations around that would sample different spots or different parts of reciprocal sphere. This would lead to different intensities, as evidenced by the gray and black spots on the right. So we would essentially see the same spot. We know which HKL value it is, but we don't know what percentage of the full intensity we could be measuring it is. So the way that this works is it uses an iterative procedure. It's able to handle only partial data. So only Bragg spots that are partial measurements. And of course, the better our data is, the better our models will be. So we're able to improve our models by essentially fine-tuning this geometry. So to begin, one thing that I found was partiality is not as straightforward as you'd think. We do know that it's going to be a ratio. It's going to tell us something about the intensities. We want to scale them. We want to know an idea of what fraction of the intensity we measured versus what we would measure if we had measured the entire sphere. So is this the percentage of the absolute max that would be measured on a single snapshot? You can think of that like this. If this is your reciprocal sphere, we've measured it right down the middle, versus if we've measured it somewhere off to the side. These could have values of 100% or full, for what would be called a partiality of 1, where essentially it's not partial, it's the full measurement, versus 50%, so it would be half the max value you could measure on a snapshot. Another way to think about it is this volume percentage of the sphere measured within the Ewald shell. If you'll remember, we don't have perfectly monochromatic beam, so this means we've got kind of a range of wavelengths that we are shooting at it. And this is exaggerated again, but you can imagine that this bandwidth is going to cause our Ewald spheres to have different curvatures. And so when measuring a spot, we could measure these, we would want to see within this kind of nest of Ewald spheres how much of our spot is being measured within them. So in this view, it would look something like that. If it's fully within the Ewald shell, then you'd have 100%, and then if it's not, you would have some fraction of that. So it turns out for this paper, we're talking about this, but I did find that you should be careful when reading because this is not, it's not always the same concept that people are talking about. They're obviously related, but so this was the first figure within the paper, and this was kind of describing the main thing, what I kind of just spoke about, but the main thing to take away from this was that although you might have different partialities within this definition, you could have essentially the same intensity measured. And this, I felt like I could illustrate a little bit better in that, so the partiality is not directly the measured intensity. If we imagine this is our Ewald sphere, and it's kind of divided up into different lines representing different energies within our bandwidth. So if I'm measuring 2 spots within this, we can see that by our definition, the partiality of these is different. The one on the right is going to have full partiality, whereas the one on the left is going to be some fraction of that. However, the intensity of these could be equivalent. And so if you think about the where you are within like kind of your Q, your scattering angle, you're going to have kind of a tighter band or a higher density of these Ewald surfaces near to kind of a low Q, whereas at high Q would have a lower density. They're more spread out. And so if you took an average for this one on the left, this would essentially be your length, or so I kind of think of it like a line integral, where if you wanted to compare what your intensity would be, that would be basically an average of all these. For the one on the right, you can think about splitting this in half and measuring one half versus the other. And so for the right half, you would get a measurement like that. The left half, you'd get like that. And so the full average would be essentially equivalent. So you would get the same intensity, even though the partiality would be different. Another thought of this would be if you're well within it, you essentially have a lower density. So again, these have almost what you call like an equivalent flux or Ewald density. So how does he calculate partiality within this? What we want to know is the intensity of the full measurement if we had measured the entire reciprocal sphere, and this is of course going to be it needs to be scaled from what we're measuring partially. And so we get our intensity partial, which is on the right side of that equation. This would be essentially what you measure. And we need to find out the factors that would scale this to the full intensity so that each shot could be comparable. So the P is the partiality, the L is something called a Lorentz factor. This kind of corrects for the distance between the limiting spheres of the Ewald. You can think of this as in where it corrects for where it is in the Q. Again, kind of going back to that density of Ewald spheres. So one way that it was done doing this to measure a full intensity, he took advantage of symmetry equivalent reflections within each image. So that's kind of what this bottom equation is. I'll go into that a little more detail here. So we've got three parts to this. One is going to be this G, which is the scaling factor. This is going to take into account some of the variations from shot to shot, such as beam parameters. We've got the measured full intensity, which is what we kind of assume after indexing, and then we would assign. I'm sorry, that actually should be partial, I believe. But the bottom part is going to be for K equivalent reflections. So within a certain snapshot, you might have multiple symmetry equivalents. You would add them up on the top. This is through this KJ summation, and then you would have to basically average them in the bottom. And so this is your initial estimate from Monte Carlo. So a few other things he talks about within this are these R high and R low, and these are essentially the radius from the middle of whatever sphere you are looking at to the edge of the resolution shells. And so you've got a high resolution and a low resolution shell. So to kind of clarify that, the low one, is going to be the one that's going to be a smaller radius, because we can remember that the radius is going to be proportional to 1 over the wavelength. So as we get a longer wavelength, we're going to have a smaller radius, and vice versa for high. So when they're talking about this, for the Lorentz factor, we can remember that this makes sense when I was saying that it measures kind of Q. So it's proportional to, that should be 1 over actually, but it's proportional to 1 over the difference between the high minus the low. And we can think of this almost like a path length here. So if we're taking this from the center to that and then minus the center to that, we're going to get something that's proportional to how thick that shell is at the point. When doing some of these calculations, though, we need to make sure that we constrain them, and this was done. And so he constrains them between R being the actual radius of the sphere you're measuring itself. We can see in this picture, for example, for A and B, both R high and R low are smaller than the actual radius. But when we get to C, we see that C is farther away from the low than it is. It's got a longer radius from it to the low resolution shell than it does through its actual the radius of the size of the spot. And then D is on both ways. And so it needs to be constrained where all of them must be between R. So when processing it, the radiuses are going to be constrained between negative R and R. So the way that the program kind of works, we take our initial data and we process with Cheetah and crystallography, and we merge the patterns, and we scale the patterns to data set iteratively to get what we assume for our full structure factors. And so at this point we have merged structure factors. What we want to do to kind of fine-tune this is minimize the difference between what we expect to see from our partials and what we're actually, so what we're calculating for our partials and what we actually are seeing. And so this delta I is going to be the difference in intensity that we see from our scaled partial that we have measured, and then what we're trying to basically find is we're trying to fine-tune this parameter P here, which is our partiality. And so these should be equivalent if everything was perfect. So what we want to do is minimize this function E, which is the summation of squares here. So G is the scaling factor. So what we do is an iterative process and keep recalculating the I full for each HKL until we get the highest agreement. So the program itself stops when the difference between the partiality of the largest difference in partiality in a given image is less than 0.01, then it will no longer fix that image, or after 10 iterations. And so for the paper, what he did was he took a structure of the PDB. It's not a trivial structure, so he did metarhodopsin 2 complex, and it's GPCR. It's got an R32 space group, so it's not lysozyme. It's not a very straightforward. I guess lysozyme's actually not that straightforward, but and then reasonable kind of parameters. So he introduced noise. He introduced the things that we're supposed to be trying to address, which would be this bandwidth, divergence, and then all of the other parameters were comparable to experiments that are actually carried out. So he generated a data set and then tried to apply the program to see if he could help post-refine it. So this is another figure in the paper. What this is essentially showing you is that he has a resolution limit where it sharply cuts off. This is from the actual data itself. But the partiality and the mean partiality both increase as you go to a lower resolution. And this makes sense if you think about the fact that you'll be farther away from you'll be farther away from where the walled spheres are all near each other, and your intensity measurements are going to be much lower than if you had been kind of near the center. And so what he did for the initial, one of the errors he introduced was errors in the reciprocal space parameters. And so for his first test, he did this with a 0.1% standard deviation on these errors. And what we can see is the improvement of data. So this top line, which he measured the R values to compare. And so the first one, it's assuming P is 1, so we assume that every image you've measured a full reflection, which we of course know is incorrect. And there was no scaling done to this, and we can see that it goes to unacceptable R values very, very quickly. The next couple of lines, he modeled it with none of this post-refinement and no scaling, and then followed by scaling but no post-refinement. And so we can see that's already drastically better. This is what we would typically do. But then when he's run the program, these bottom two, he's run it for a cycle of 1 and 3 cycles for the post-refinement, and it drastically improves our data, which we can see by the R values staying low to a much higher resolution. And so this shows the fine-tuning really can, the geometry really can improve your data quite a bit, even after a very short number of cycles through this. Another thing that was shown in here was, so this is what we were comparing, the minimization. And so part A of this figure is showing before any post-refinement. This shows what our observed and calculated partialities are, and we can see that it's somewhat linear, but there is quite a wide variation. It's not very tight. Even after one iteration, though, which we can see in B, you get a marked improvement and agreement between what your calculated partiality and what you're actually observing within your patterns. After 3, it gets tighter even still. And so he also did this with a higher error in the reciprocal space. So instead of the 0.1, he did a 1.0, and we can see this is even more drastic improvement. So it's going to be the same lines that we saw prior as far as their meaning. But we can see that they're all kind of going to unacceptable R values at 4, 3.5 angstroms, where after 1 cycle of refinement, we're able to extend it, and then after 3, even more so. It's much more drastic. So this is a tool that can certainly be used to help your data and maybe extend your confidence in your resolution when you're making a model. So what's next? And they mentioned in the paper, in the future, they want to apply this to real data. but it turns out that this was written in 2014, so that would mean that the future is already here. So this has been implemented in some data sets already. People have been using it. It's one of the tools within the crystallography suite, and it's been applied in some work, but none of it has been published yet. So I'm not able to speak of any of the ones that I know of, and I'm sure there's some that I don't as well. But it should be coming soon to some papers near you. So keep your eyes open, and I'm sure we can see kind of past just a model and some computational stuff. We can see it actually applied to real data and see kind of the improvements that can be made with it. So with that, I'll take any questions, and thank you for your time.